Good evening, and welcome. Tonight, as the world around you gradually grows quieter, and the concerns of the day begin to fade into the distance, like footsteps disappearing along an old stone road after sunset, I invite you to settle into a comfortable place, breathe slowly, and allow your imagination to wander across a span of time so immense that even the longest chapters of human history become almost impossible to notice against its endless horizon. For our journey this evening is not measured in centuries, nor in kingdoms, nor even in the countless generations that separate us from the first villages or the earliest cities, but instead stretches backwards through millions upon millions of years into an earth so ancient that no human voice had ever spoken, no campfire had ever illuminated the darkness, and no familiar landscape had yet taken the form we recognize today. Imagine, for just a moment, standing upon a lonely shoreline as the sun slowly sinks below an unfamiliar horizon, where strange plants sway in a warm breeze unlike any wind that blows across our modern world. Enormous insects drift lazily through humid forests. Distant volcanoes release gentle columns of smoke into a sky untouched by aircraft, and every sound comes from creatures that vanished long before humanity ever dreamed of building cities, writing books, or wondering about its own past. Now imagine asking a single quiet question. What if, long before the first human looked toward the stars, long before the first stone tool was shaped by careful hands, long before the first fire warmed a family gathered beneath the night sky, another civilization had already risen, prospered, changed the planet, and then disappeared so completely that almost nothing remained, except perhaps a few subtle whispers hidden within the rocks themselves? It sounds like the beginning of an ancient legend, yet the remarkable thing about the Silurian hypothesis is that it is not presented as mythology or fantasy, but as an exercise in scientific reasoning, encouraging researchers to ask what traces an industrial civilization would actually leave behind if enough time, perhaps 50 million years, 100 million years, or even more, were allowed to erase almost every visible reminder of its existence. As we travel deeper into Earth's past, the stranger time itself begins to feel, because human history, which often seems unimaginably ancient to us, occupies only the smallest fraction of our planet's lifetime, resembling less a great epic and more like a single page placed at the very end of an impossibly thick volume, whose earlier chapters have mostly been lost, weathered away, rewritten by mountains, oceans, glaciers, earthquakes, and the slow but relentless movement of continents drifting across the surface of the Earth. Perhaps by the end of tonight's journey, we will not discover evidence that an unknown civilization truly existed before humanity, because no such evidence currently does exist, yet we may discover something equally meaningful, namely that the Earth itself possesses an astonishing ability to reshape its own history, gently smoothing away the marks left by even the greatest events, until only faint geological fingerprints remain for future scientists to interpret with patience, humility, and curiosity. So dim the lights if you wish. Allow your breathing to become slow and steady. Imagine the stars shining above an Earth that has witnessed nearly 4.5 billion years of change, and let us begin. There are certain questions that appear almost childlike when first spoken aloud, questions so wonderfully simple that they invite an immediate answer before quietly revealing depths far greater than anyone first expected. And among these rare questions is one that has fascinated scientists, philosophers, historians, and dreamers alike. If another technological civilization had truly existed millions of years before humanity, would we still be able to recognize the evidence today? Or would time itself have erased nearly every trace until the planet seemed as though nothing extraordinary had ever happened at all? To appreciate the scale of this question, we must first step away from the ordinary rhythm of human history and instead adopt the perspective of the Earth itself, whose memory extends so far beyond our own that entire mountain ranges have risen and vanished, while countless species appeared, flourished, and disappeared, without leaving behind anything more than scattered fossils pressed into ancient stone. Human beings often think in terms of decades, occasionally in centuries, and sometimes in thousands of years when reflecting upon civilizations like Egypt, Mesopotamia, China, or Rome. Yet the Earth measures time differently, for it has watched continents drift across thousands of kilometers, oceans open and close, climates transform from tropical warmth to frozen ice ages, and entire ecosystems vanish before new ones slowly emerged to replace them, making even the oldest human monuments seem remarkably young. Consider one of the most famous structures ever built by our species. The Great Pyramid of Giza has stood for more than 4,000 years, surviving storms, invasions, changing dynasties, and countless generations who have looked upon its towering stones with admiration. Yet, from the perspective of geology, those 4,000 years represent almost nothing at all, for they are scarcely noticeable within the millions of years that define Earth's natural processes. Imagine placing a single grain of sand on an enormous beach stretching beyond the horizon. That solitary grain would still represent a larger proportion of the beach than human civilization represents within the age of our planet. Such comparisons remind us not of our insignificance, but rather of the extraordinary depth of Earth's history, whose earliest chapters unfolded so long ago that they challenge our imagination almost beyond its limits. If another technological civilization had truly existed 100 million years before humans, it would not simply be ancient by our standards, it would be unimaginably ancient. Its cities would have faced not merely centuries of decay, but tens of millions of years during which mountains could collapse, oceans open and close, climates transform from tropical warmth to frozen ice ages, and entire ecosystems vanish before new ones slowly emerged to replace them, making even the oldest human monuments seem remarkably young. This realization leads naturally towards a surprising possibility. Perhaps asking whether ancient cities should still exist is the wrong question. Perhaps the better question is whether anything at all could survive such immense stretches of time. Would concrete remain? Would steel endure? Would glass survive? Would radioactive materials linger? Would microscopic chemical changes persist within the rocks themselves long after every building had vanished? These questions eventually inspired scientists to consider not visible ruins, but invisible signatures, subtle clues preserved within geological records, much like faint fingerprints remaining after everything else had been carefully cleaned away. The Earth rarely preserves complete stories. Instead, it preserves fragments, a shell here, a fossilized leaf there, a thin layer of volcanic ash, tiny changes in atmospheric chemistry trapped inside ancient ice or buried sediments. Like detectives investigating an event that occurred unimaginably long ago, geologists rarely expect perfect evidence. Instead, they patiently assemble countless small observations into coherent explanations. Sometimes those explanations reveal asteroid impacts. Sometimes they reveal ancient climates. Sometimes they reveal long-lost oceans, and occasionally they encourage scientists to ask whether entirely unexpected possibilities deserve at least thoughtful consideration, not because they are likely, but because examining them teaches us how Earth's memory truly works. The Silurian hypothesis belongs within this tradition of scientific curiosity. It is less an attempt to prove a forgotten civilization than an invitation to understand what evidence would actually remain if one had ever existed. In many ways, the hypothesis becomes a mirror reflecting our own civilization back towards us, encouraging us to consider what traces modern humanity might leave behind after tens of millions of years have passed and every familiar city has long since disappeared beneath the slow and patient work of geological time.
Long before human beings learned to cultivate crops, construct temples, or chart the movements of the stars across the night sky, the Earth had already lived through an history so astonishingly long and dynamic that our entire species occupies only the briefest closing moments of an immense planetary story whose earliest chapters unfolded beneath skies unlike any we have ever known. Approximately 4.5 billion years ago, the young Earth was a world of extraordinary violence where colossal impacts, oceans of molten rock, and relentless volcanic activity gradually transformed a newly formed planet into one capable of supporting liquid water, stable continents, and eventually the earliest forms of life whose humble beginnings would ultimately shape every ecosystem that followed. Life itself did not appear overnight. Instead, it emerged through unimaginably slow processes extending across hundreds of millions of years, during which tiny microscopic organisms quietly altered the chemistry of the atmosphere, releasing oxygen that slowly accumulated until complex multicellular life finally became possible. These first living organisms possessed neither intelligence nor ambition in any human sense, yet together they transformed an entire planet. Countless generations lived and died without leaving monuments, stories, or written records, but their collective activity permanently changed Earth's atmosphere, demonstrating that life need not build cities to reshape the world. Hundreds of millions of years later came the extraordinary diversification known today as the Cambrian explosion, when an astonishing variety of complex animals appeared within the oceans, experimenting with countless body forms, survival strategies, and ecological relationships, many of which vanished forever, while others eventually gave rise to familiar branches of life that continue to exist today. The continents themselves refused to remain still. Driven by slow currents within Earth's mantle, enormous landmasses drifted steadily across the globe, sometimes joining together into vast supercontinents before gradually breaking apart once more, carrying mountains, rivers, forests, and entire ecosystems across different climates over spans of time almost impossible for human imagination to grasp. There were periods when tropical forests covered regions that today lie near the poles. There were ages when deserts occupied lands now hidden beneath oceans. Sea levels rose and fell repeatedly, drowning coastlines before exposing them once again. Glaciers advanced across continents before retreating into memory. Volcanoes built islands that eventually disappeared beneath waves. Nothing remained fixed. Everything changed. Dinosaurs eventually dominated the land for more than 160 million years, an astonishing reign compared with humanity's comparatively brief existence. Yet even they ultimately disappeared after a catastrophic asteroid impact, combined with other environmental pressures, transformed Earth's ecosystem so dramatically that entirely new evolutionary opportunities emerged for mammals, birds, and eventually our own distant ancestors. When viewed from this immense perspective, humanity appears not at the center of Earth's story, but near its latest pages. Modern Homo sapiens have existed for roughly 300,000 years. Agriculture began only around 12,000 years ago. Industrial civilization occupies little more than 2 centuries. The entire age of electricity, automobiles, computers, and satellites represents an almost invisible moment within geological history. Understanding this perspective is essential because it reminds us that Earth existed for billions of years before us and will almost certainly continue existing for billions more after our own civilization eventually changes into forms we cannot yet imagine. The planet is not static, it is endlessly creative. Mountains become plains, oceans become deserts, deserts become forests, species evolve, species disappear. The Earth patiently continues its quiet transformation regardless of who happens to inhabit its surface at any particular moment. Against such an immense backdrop, asking whether another civilization could once have existed becomes less about fantasy and more about appreciating just how thoroughly geological processes reshape the world over extraordinary lengths of time.
The name Silurian Hypothesis possesses almost mythical quality, leading many people to imagine forgotten kingdoms inhabited by mysterious beings whose cities now lie buried beneath ancient stone. Yet the true origin of the name is far more playful and surprisingly modern, reflecting the curiosity and imagination that often accompany serious scientific discussion. The hypothesis was proposed in 2018 by 2 scientists, the astrophysicist Adam Frank and climate scientist Gavin A. Schmidt, who were not attempting to argue that prehistoric industrial civilizations actually existed, but were instead asking a remarkably practical scientific question, inspired by both geology and the search for intelligent life elsewhere in the universe. Its unusual name comes from the fictional reptilian race known as the Silurians from the long-running British science fiction television series Doctor Who, in which intelligent creatures are imagined to have inhabited the Earth long before humanity. And although the scientists borrowed the name with a sense of humor, the hypothesis itself remains entirely grounded in real geological science rather than fictional storytelling. At its heart, the Silurian hypothesis asks a surprisingly simple question. If an industrial civilization had existed many millions of years before humans, what evidence would still remain today? Notice how carefully the question is framed. It does not ask whether such a civilization definitely existed. It asks what detectable signatures scientists should expect to find if one had existed. This distinction is extraordinarily important because science advances not merely by collecting facts, but by asking questions that, at least in principle, can be investigated through observation and evidence. Imagine discovering a distant planet orbiting another star. Suppose astronomers noticed unusual chemical compounds in its atmosphere, unexpected changes in carbon isotopes, or pollutants that appeared difficult to explain through purely natural geological activity alone. How could scientists determine whether those observations resulted from intelligent life rather than purely natural processes? Answering that question requires understanding how industrial civilizations alter planets. And to understand that, researchers first asked what traces our own civilization would leave behind. Would future geologists living 50 million years from now recognize the brief industrial age? Would they identify fossil fuels burned by humanity? Would unusual plastics survive? Would artificial radioactive elements remain? Would sudden changes in atmospheric carbon become visible inside ancient sediments? The Silurian hypothesis therefore becomes deeply relevant not only to Earth's past, but also to the growing scientific effort to search for technological civilizations beyond our own solar system. It transforms an apparently impossible historical mystery into a practical scientific framework. Interestingly, once researchers began thinking along these lines, they discovered that many familiar assumptions deserved reconsideration. Buildings disappear surprisingly quickly. Roads crumble. Metal corrodes. Even reinforced concrete eventually fractures under the combined influence of water, freezing temperatures, chemical reactions, earthquakes, and plant roots. Given enough millions of years, almost every visible structure humanity has built would almost certainly vanish. What might remain instead are subtle chemical fingerprints embedded within rocks and sediments, tiny anomalies that future scientists could recognize only through careful laboratory analysis rather than dramatic excavation. This realization changes the entire conversation. Instead of searching for buried skyscrapers beneath dinosaur fossils, scientists examine isotope ratios, sedimentary layers, atmospheric chemistry, extinction events, and long-term environmental changes. The investigation becomes quieter, more patient, more scientific, and perhaps even more fascinating. For now, however, the evidence available to modern science remains remarkably clear. No confirmed geological signature has demonstrated the existence of an industrial civilization before humanity. The hypothesis remains exactly what its creators intended it to be: a thoughtful scientific exercise that sharpens our understanding of Earth's geological record, while helping researchers imagine how technological civilizations, whether on Earth or on distant worlds, might leave traces that survive long after every city has disappeared. As our journey continues, we will begin to explore the remarkable power of geological time itself, discovering why the Earth is capable of preserving certain memories for hundreds of millions of years, while quietly erasing countless others, until even the greatest achievements may become little more than whispers hidden within ancient stone. When people first encounter the Silurian hypothesis, their initial reaction is often one of surprise, followed quickly by curiosity, because it seems unusual that respected scientists would devote serious thought to a question that appears at first glance to belong more comfortably within the pages of science fiction than within academic journals. Yet the true motivation behind the hypothesis has very little to do with proving extraordinary claims, and everything to do with improving our understanding of planets, civilizations, and the subtle fingerprints that intelligent life might leave behind across immense stretches of time. Science has always advanced by asking careful questions rather than by protecting comfortable assumptions. And throughout history, many ideas that once appeared strange eventually became accepted because researchers were willing to investigate them patiently instead of dismissing them immediately, while many other ideas were shown to be incorrect through the same careful process, demonstrating that the purpose of science is not to defend a particular conclusion, but to follow evidence wherever it leads, even if that journey ultimately returns us to the understanding we began with, only now supported by stronger reasoning and clearer knowledge. This spirit of curiosity becomes especially important when scientists consider one of the greatest questions humanity has ever asked:
Are we alone in the universe, or have technological civilizations arisen elsewhere among the countless stars that fill the night sky? Modern astronomy has revealed that our galaxy alone contains hundreds of billions of stars, many of which possess planets orbiting within regions where liquid water could potentially exist, while observations over the past few decades have confirmed that planets themselves are remarkably common throughout the cosmos, suggesting that planets similar in size to Earth may number in the billions across the Milky Way alone. Yet discovering a distant planet is only the beginning of a much larger challenge. Suppose astronomers observe an Earth-sized world orbiting a distant star and detect unusual gases within its atmosphere, or perhaps notice rapid chemical changes that seem difficult to explain through known natural processes alone.
When people first encounter the Silurian hypothesis, their initial reaction is often one of surprise, followed quickly by curiosity, because it seems unusual that respected scientists would devote serious thought to a question that, at first glance, belongs more comfortably within the pages of science fiction than within academic journals. Yet the true motivation behind the hypothesis has very little to do with proving extraordinary claims and everything to do with improving our understanding of planets, civilizations, and the subtle fingerprints that intelligent life might leave behind across immense stretches of time. Science has always advanced by asking careful questions rather than by protecting comfortable assumptions, and throughout history, many ideas that once appeared strange eventually became accepted because researchers were willing to investigate them patiently instead of dismissing them immediately, while many other ideas were shown to be incorrect through the same careful process, demonstrating that the purpose of science is not to defend a particular conclusion, but to follow evidence wherever it leads, even if that journey ultimately returns us to the understanding we began with, only now supported by stronger reasoning and clearer knowledge. This spirit of curiosity becomes especially important when scientists consider one of the greatest questions humanity has ever asked: are we alone in the universe, or have technological civilizations arisen elsewhere among the countless stars that fill the night sky? Modern astronomy has revealed that our galaxy alone contains hundreds of billions of stars, many of which possess planets orbiting within regions where liquid water could potentially exist, while observations over the past few decades have confirmed that planets themselves are remarkably common throughout the cosmos, suggesting that planets similar in size to Earth may number in the billions across the Milky Way alone. Yet discovering a distant planet is only the beginning of a much larger challenge. Suppose astronomers observe an Earth-sized world orbiting a distant star and detect unusual gases within its atmosphere, or perhaps notice rapid chemical changes that seem difficult to explain through known natural processes alone. How would they determine whether those changes were produced by volcanoes, oceans, microscopic life, forests, or an advanced civilization capable of altering its environment through industry and technology? The answer is far from simple, because nature itself is extraordinarily creative, often producing chemical signatures that appear unusual until a deeper understanding reveals perfectly natural explanations, meaning that scientists must first understand every possible natural process before confidently identifying evidence of intelligent activity. This realization gradually led researchers toward an unexpected thought.
Instead of attempting to recognize technological civilizations on distant planets, perhaps they should first ask what unmistakable traces our own civilization is leaving upon Earth. At first, this appears to be an easy question. After all, modern humanity has constructed enormous cities visible from aircraft, networks of highways crossing continents, thousands of satellites orbiting the planet, millions of kilometers of electrical cables, dams that redirect rivers, mines reaching deep beneath mountains, and countless buildings made from steel, concrete, glass, and plastic. Surely such achievements would remain visible forever. Yet geology tells a different story. The Earth is not a museum designed to preserve human accomplishments. Instead, it is an active planet whose surface is constantly reshaped by weather, rivers, glaciers, earthquakes, volcanoes, shifting coastlines, and the slow but relentless movement of tectonic plates, each process quietly working year after year, century after century, and million after million of years, until even the most durable structures eventually surrender to time. Imagine walking through an abandoned village hidden deep within a forest. At first, the buildings remain recognizable. Roofs begin to collapse, wood decays, stone walls crack apart. Seeds carried by the wind find small openings where rainwater has collected. Tiny roots push gently into those cracks. Year after year, the roots grow thicker, the walls lean, the floors disappear beneath fallen leaves. Trees rise where streets once crossed. After only a few centuries, nature has already begun to reclaiming the landscape. Now imagine not hundreds of years, but 100,000, then 1 million, then 50 million. The imagination struggles to comprehend such durations because they exceed every ordinary measure of history. Entire mountain ranges rise and disappear during those intervals. Coastlines migrate hundreds of kilometers. Oceans open and close. Sediments accumulate layer upon layer until ancient landscapes lie buried beneath thousands of meters of rock. Seen from this perspective, the remarkable question is not whether cities disappear. The remarkable question is whether anything survives at all. This became one of the central motivations behind the Silurian hypothesis. Instead of asking whether prehistoric skyscrapers might still exist, scientists began asking which changes produced by an industrial civilization could remain detectable after unimaginable spans of geological time. And that shift in perspective transformed the entire discussion from speculative storytelling into a practical scientific investigation rooted firmly within geology, chemistry, climatology, and planetary science. In many respects, the hypothesis became a mirror through which humanity examined itself. By wondering what future scientists might someday discover about us, researchers also learned how surprisingly delicate our civilization truly is when measured against the quiet persistence of the Earth itself. The roads we travel every day, the cities that seem permanent, the bridges spanning mighty rivers, and even the tallest buildings reaching confidently towards the clouds all exist within only a fleeting moment of geological history, reminding us that permanence is often an illusion created by the brevity of human lifetimes rather than a property of the structures themselves. Perhaps that realization is one of the hypothesis' greatest gifts. It gently encourages humility. It reminds us that civilizations rise within nature, not outside it, and that every achievement, no matter how magnificent, ultimately becomes part of the same planetary story that has been unfolding for billions of years. Imagine standing in the center of today's great cities during the quiet hours before dawn, when the streets remain almost empty. The lights shimmer softly against sky towers. Trains rest silently within underground tunnels, and thousands of buildings stand together like an artificial mountain range, created not by tectonic forces, but by countless human hands working across generations. It is easy, while surrounded by such immense structures, to believe that they possess a kind of permanence. Steel appears strong, concrete appears solid, stone appears eternal, glass reflects the sky with quiet confidence. Yet every one of these materials is already changing. Even now, while people sleep peacefully within apartments and homes, invisible chemical reactions continue without pause. Steel slowly oxidizes wherever moisture reaches its surface. Concrete develops microscopic fractures as temperatures rise and fall. Glass gradually weathers under the influence of water and airborne particles. Plants search patiently for the smallest cracks through which roots may begin their silent work. Nothing remains entirely unchanged. The Earth does not destroy civilizations through sudden violence alone. More often, it accomplishes its work through extraordinary patience. Rain falls one drop at a time. Wind carries tiny grains of sand. Rivers transport microscopic particles toward distant oceans. Frost expands inside narrow cracks before melting once again. Each individual event seems insignificant. Together, they reshape mountains. Archaeologists frequently discover ruins only a few thousand years old, whose walls have already collapsed into scattered stones, difficult to distinguish from surrounding landscapes. Ancient roads vanish beneath soil. Wooden structures decay completely. Even massive temples require continuous maintenance if they are to survive. Without human care, every monument begins a slow conversation with nature, and nature never hurries. Now, let us imagine far greater intervals, 100,000 years. During such a period, climates may change dramatically. Forests spread across abandoned cities. Rivers carve entirely new channels. Sea levels rise or fall. Glaciers advance across northern continents, grinding rock beneath thousands of meters of moving ice. The landscape itself begins forgetting where human settlements once stood. After 1 million years, the transformation becomes almost unimaginable. Many coastlines disappear beneath the sea. New coastlines emerge elsewhere. Volcanic ash buries ancient valleys. Earthquakes fracture entire regions. Layers of sediment accumulate above forgotten plains. What once stood proudly beneath open skies now lies hidden beneath hundreds of meters of mud, sand, limestone, or volcanic deposits. Extend the clock further still. 10 million years, 50 million years, 100 million years. Continents have drifted. Mountains have risen. Mountains have eroded away. Entire ocean basins have expanded or disappeared. Rocks once exposed to sunlight have sunk deep beneath the crust, where heat and pressure gradually transform them into entirely different forms. Some eventually melt. Others return to the surface through volcanic activity. The Earth continuously recycles its own outer layers with astonishing efficiency. In such a world, what chance does a city truly possess? Surprisingly little. The buildings themselves would almost certainly vanish. Steel returns to iron oxides. Concrete crumbles into fragments before those fragments become sediments. Roads crack apart. Subways collapse. Dams fail. Reservoirs fill with sediment until rivers reclaim their ancient paths. Even the outlines of entire metropolitan regions become almost impossible to recognize. This conclusion may initially seem discouraging, yet it reveals something profoundly beautiful about the natural world. Nature is not hostile toward civilization, it is simply patient beyond anything humans normally experience. Given sufficient time, forests reclaim abandoned villages, coral reefs grow across sunken ships, deserts swallow roads, moss softens stone. The earth heals every scar, not because it intends to erase history, but because change itself is the normal condition of our living planet. For this reason, scientists studying the Silurian Hypothesis rarely expect visible ruins to survive across tens of millions of years. Instead, they search for something much more subtle. Not cities, not towers, not monuments, but signatures. Tiny alterations in chemistry, unexpected isotope ratios, artificial compounds buried within sediments, minute clues capable of surviving long after every recognizable structure has disappeared. The greatest evidence of a civilization may therefore be invisible to the naked eye. Its memory may persist not in architecture, but within the atoms themselves.
If the earth could speak, it would not tell its story through written words, carved monuments, or carefully preserved libraries, but through layers of stone, quietly resting one above another, each containing fragments of ancient environments that together form a vast archive extending backward across nearly the entire history of our planet. Although, like every ancient archive, it is incomplete, weathered, and filled with missing pages that have long since been lost. Geologists often describe rocks as pages within an enormous history book. Yet, unlike the books resting peacefully upon library shelves, Earth's volume is constantly being edited even as it is being written, with rivers removing chapters, volcanoes adding new ones, tectonic plates folding older pages beneath younger layers, and erosion sometimes exposing forgotten passages that remained hidden for hundreds of millions of years. Every sedimentary rock begins with something remarkably ordinary. Tiny grains of sand settle on a riverbed. Fine mud drifts quietly through still water before resting upon the bottom of a lake. Minute shells accumulate across the floor of an ancient sea. Leaves fall into wetlands. Volcanic ash settles gently across distant landscapes. Year after year, these materials gather almost unnoticed. Century after century, they become thicker. Eventually, pressure compresses them into stone. Within those rocks remain delicate records of vanished worlds. Fossils preserve the shapes of animals that walked beneath unfamiliar skies. Pollen grains reveal forests that disappeared long ago. Chemical compositions record ancient temperatures. Tiny bubbles trapped inside minerals preserve clues about the atmosphere itself. The geological record does not remember everything equally well. Some environments preserve extraordinary detail. Others preserve almost nothing. Imagine writing a message upon dry sand beside the ocean. For a short time, the words remain perfectly clear. Then waves arrive. Soon, nothing remains.
Now imagine carving the same message deeply into solid granite. It survives much longer. The geological record functions similarly. Certain events become beautifully preserved. Others disappear almost immediately. This uneven preservation creates one of the greatest challenges facing Earth scientists. Absence of evidence does not always mean evidence of absence. Sometimes the relevant rocks no longer exist. Sometimes they remain buried kilometers beneath the surface. Sometimes erosion removed them long ago. Sometimes no sediments formed where an event actually occurred. Every geological conclusion, therefore, requires careful interpretation rather than certainty alone. Researchers compare rock layers collected from different continents. They measure isotope ratios with astonishing precision. They identify microscopic fossils, invisible without powerful microscopes. They reconstruct ancient climates from chemical signatures preserved within minerals scarcely larger than grains of dust. Patiently, piece by piece, they rebuild stories whose original landscapes vanished millions of years before humans appeared. This remarkable archive has revealed asteroid impacts, ancient supercontinents, repeated ice ages, enormous volcanic eruptions, shifting sea levels, and countless episodes of biological evolution. It has shown that Earth's climate has changed many times. It has documented mass extinctions affecting nearly every form of life. It has preserved evidence of creatures whose bones remained hidden until erosion finally revealed them after unimaginable spans of time. Yet, despite all this remarkable information, the geological record remains selective. It whispers rather than shouts. It offers clues instead of complete explanations. For scientists considering the Silurian hypothesis, this imperfect memory becomes the central focus of investigation. If an industrial civilization existed tens of millions of years ago, what kind of geological signature would survive within this vast but incomplete archive? Would unusual carbon concentrations remain? Would synthetic materials leave microscopic traces? Would industrial pollution alter sediment chemistry? Or would natural geological processes eventually blur every distinction until civilization became indistinguishable from the countless other events already recorded within Earth's ancient stones? These questions possess no simple answers. Instead, they invite careful observation, patient experimentation, and thoughtful debate. Perhaps the greatest lesson offered by Earth's geological memory is not that it preserves everything, but that it preserves just enough for curious minds to continue asking meaningful questions. Every fossil discovered beneath a hillside, every ancient shell embedded within limestone, every layer of volcanic ash spread across distant continents, every subtle shift in carbon preserved within sedimentary rocks. Together, they remind us that the Earth has always been writing its history, long before humans learned to write their own. And somewhere within those ancient pages, whether they contain only evidence of nature's astonishing creativity or something even more unexpected, scientists continue reading with quiet patience, knowing that the next discovery may come not from dramatic ruins rising above the landscape, but from a single microscopic clue hidden within a fragment of stone that has waited hundreds of millions of years to tell its small part of a much larger story.
If there is one place on Earth that truly teaches us humility, it is not the summit of the tallest mountain or the endless expanse of the driest desert, but the quiet floor of the deep ocean, where darkness has reigned for millions of years, where sunlight has never reached, and where countless chapters of our planet's history lie buried beneath layer after layer of fine sediment, patiently accumulating grain by grain until entire worlds disappear beneath a blanket of geological time. When we look at a modern map of Earth, with its familiar arrangement of continents and oceans, it is easy to believe that these great land masses have always occupied roughly the same positions, separated by coastlines that seem almost permanent in our daily experience. Yet nothing could be further from the truth, because the surface of our planet is constantly moving, although at a pace so slow that a human lifetime is far too brief to notice the change without careful scientific measurement. The continents drift only a few centimeters each year, moving no faster than the growth of a finger finger. Yet, given millions of years, those seemingly insignificant movements carry entire mountain ranges across climates, close ancient seas, open new oceans, and completely rearrange the geography of the planet. Imagine watching a time-lapse film that spans 200 million years instead of 2 hours. The continents would no longer appear solid and unmoving. Instead, they would resemble enormous rafts slowly floating across a restless sea of molten rock hidden far below the Earth's crust, sometimes colliding with tremendous force to build towering mountain chains, sometimes separating to create new ocean basins, and sometimes sliding silently past one another while earthquakes marked their invisible boundaries. Long before humanity appeared, there existed vast supercontinents unlike anything we see today. One of the most famous was Pangaea, a colossal landmass that gathered nearly all of Earth's continents into a single enormous body surrounded by a global ocean. For millions of years, animals wandered across landscapes that today belong to entirely different continents, because those continents had not yet begun their long journey toward their present positions. Eventually, Pangaea itself began to fracture. Great rifts opened, volcanoes erupted, new seas flooded into widening valleys. Slowly, almost imperceptibly, the familiar continents of today were born. North America drifted away from Europe. Africa separated from South America. India traveled northward across an entire ocean before colliding with Asia and raising the Himalayas toward the sky. These transformations remind us that the Earth never remains still for long. Coastlines migrate. Islands appear and vanish. Entire shallow seas flood across continents before retreating once more. Regions that were once tropical beaches eventually become snowy mountain peaks, while ancient deserts sink beneath warm oceans where coral reefs quietly flourish. For the Silurian hypothesis, this constant motion carries profound implications. Suppose an ancient civilization had built magnificent coastal cities tens of millions of years ago. Where would those cities be today? Many people instinctively imagine buried ruins hidden beneath forests or deserts, waiting for archaeologists to uncover them with careful excavation. Yet geology offers a different possibility. Some ancient coastlines no longer exist. They have been submerged beneath the sea. Others have been pushed beneath neighboring tectonic plates in a process known as subduction, where oceanic crust slowly descends into Earth's mantle and is gradually destroyed by extraordinary heat and pressure. This process is among the most powerful recycling systems on our planet.
Unlike the continents, which can preserve rocks billions of years old, most oceanic crust survives only about 200 million years before disappearing forever beneath another tectonic plate. The seafloor itself is continually renewed. New crust forms at mid-ocean ridges as molten rock rises from below. Older crust moves outward like a slow conveyor belt. Eventually, it sinks once more into the mantle, where its ancient history is largely erased. Imagine writing a story upon a sheet of paper that is steadily moving toward a great fire. For a time, the words remain readable. Eventually, the edges begin to burn. Soon, the entire page disappears. Oceanic crust experiences something remarkably similar. Its history is constantly recycled. If an industrial civilization had developed primarily upon coastlines bordering ancient oceans hundreds of millions of years ago, many of its physical traces could have been carried into the mantle long before humanity evolved. The evidence would not merely be buried, it would be destroyed. This realization reveals why geologists often focus their attention upon stable continental interiors rather than ancient seafloors when searching for the oldest surviving rocks, because some regions of continents have remained remarkably stable for billions of years, preserving fragments of Earth's earliest history that would never survive beneath the constantly recycled ocean floor. Yet even continental rocks tell incomplete stories. Erosion removes layers. Sediments bury landscapes. Mountain building compresses ancient formations until they become almost unrecognizable. The Earth remembers, but never perfectly. As we drift quietly through this immense ocean of time, one gentle truth becomes increasingly clear. The greatest force working against the survival of ancient civilizations is not catastrophe. It is the ordinary, patient movement of the planet itself, continuing day after day, century after century, million after million of years, until entire coastlines vanish without leaving even the faintest outline on the modern map of the world.
When we stand before a great mountain, its rocky slopes stretching confidently towards the clouds, while rivers wind patiently through the valleys below, it is difficult to imagine that such immense landscapes could ever disappear, for mountains possess an appearance of permanence that seems almost eternal, while rivers appear destined to follow the same familiar paths forever. Yet the Earth tells a quieter story, one in which even the grandest landscapes eventually surrender to time with extraordinary patience rather than dramatic speed. Mountains are not permanent monuments. They are temporary expressions of the restless forces operating deep within our planet. Born through collisions between continents, uplifted by tectonic pressure, or raised by volcanic activity, they begin eroding almost from the very moment they first emerge. Rain falls on exposed stone. Winter ice expands within tiny cracks. Summer heat causes minerals to expand and contract. Wind carries fine particles across exposed ridges. Plants extend roots into fractures invisible to the human eye. Each individual change seems almost meaningless. Together, they reshape entire continents. Imagine observing a single granite cliff over the course of one afternoon. Nothing appears to change. Observe the same cliff across 1 century. Small fragments have fallen. Observe it across 100,000 years. Its sharp edges soften. Observe it across 100 million years.
perhaps little remains except a broad plain beneath which ancient roots of the original mountain still lie hidden. Geologists sometimes refer to these deeply eroded remnants as the roots of vanished mountain ranges, because while the towering peaks disappear, the harder rocks buried far below often survive long after everything visible has been worn away. This extraordinary cycle has repeated countless times throughout Earth's history. Entire mountain systems have risen higher than anything we see today before erosion gradually reduced them to gentle landscapes almost impossible to recognize as former giants. Even the mighty Himalayas, still growing as India continues pressing into Asia, will someday begin a similar journey toward disappearance, although that process lies far beyond any timescale relevant to human civilization. Rivers contribute quietly to this endless transformation. Although they often appear peaceful, rivers are among the most powerful sculptors on Earth. Every drop of flowing water carries tiny grains of sand. Each grain acts like a miniature tool polishing stone. Over thousands of years, rivers carve valleys. Over millions of years, they reshape entire regions. They transport enormous quantities of sediment toward lakes, deltas, and oceans, gradually burying older landscapes beneath fresh deposits. The Nile, the Mississippi, the Amazon, the Yangtze, each has carried unimaginable volumes of sediment throughout its history. Those sediments settle layer upon layer. Ancient forests disappear beneath them. Old river channels become invisible. Entire floodplains vanish beneath younger deposits. The landscape slowly rewrites itself. Now imagine a city built beside one of these rivers. At first it prospers. Centuries pass. The river changes course. Floods deposit fresh layers of mud. Buildings collapse. Vegetation spreads. Eventually, the settlement lies buried beneath sediments so thoroughly that future generations no longer realize a city once occupied the site. Archaeologists encounter such examples even within the relatively brief span of human history. How much more complete would the burial become after 50 million years? Perhaps astonishingly complete. Some ancient river systems no longer exist at all. Others have reversed direction because mountain ranges rose or collapsed. Still others became buried beneath lava flows or submerged beneath shallow seas. The rivers themselves moved on, leaving behind only subtle clues preserved within ancient rock formations. For scientists considering the Silurian hypothesis, these observations offer another important lesson. Civilizations tend to flourish beside rivers. Fresh water supports agriculture. Transportation becomes easier. Trade expands. Settlements grow. Yet the very rivers that nurture civilizations also become agents of their gradual disappearance. Without maintenance, canals fill with sediment. Harbors become marshes. Floodplains bury abandoned buildings. Stone foundations vanish beneath fertile soils. What once served life eventually conceals its remains. Nature rarely acts with sudden finality. Instead, she works gently, patiently, persistently. Every river carries away a little more stone. Every storm moves another layer of soil. Every growing forest covers another forgotten road. Every century adds another page to the geological archive while quietly obscuring the pages beneath. The disappearance of mountains and rivers teach us something profound. Earth's surface is not a fixed stage upon which history unfolds. It itself is one of history's most active participants, constantly editing the landscapes upon which every civilization, every ecosystem, and every generation briefly lives before becoming part of the much longer story of the planet.
When imagining the distant future, many people naturally assume that at least a few familiar objects from modern civilization must surely survive for millions upon millions of years. Perhaps a towering skyscraper standing lonely against an empty horizon, a bridge stretching across a forgotten river, or great monuments built from concrete and steel, waiting silently for distant descendants to rediscover them. Yet the reality revealed by geology and materials science is both more subtle and in many ways more fascinating than these familiar images suggest. Let us begin with steel. Modern civilization depends upon it almost everywhere. Steel supports buildings, it forms bridges, it strengthens concrete, it carries electricity, it allows ships to cross oceans and trains to cross continents. To human eyes, steel appears remarkably durable, yet steel possesses one persistent weakness. It longs, in a chemical sense, to return toward the oxidized minerals from which it was originally extracted. Rust is not merely damage, it is steel slowly returning to a more stable natural state. Moisture, oxygen, salt, changing temperatures, and microorganisms all contribute to this gradual transformation. Without maintenance, exposed steel weakens steadily. After centuries, much has disappeared. After thousands of years, very little remains. Across millions of years, recognizable steel structures would almost certainly vanish entirely. Concrete tells a similar story. At first glance, it seems almost indestructible. Roman aqueducts and ancient harbors demonstrate that carefully prepared concrete can survive for thousands of years under favorable conditions. Yet concrete also develops fractures. Water penetrates tiny cracks, minerals dissolve, freeze-thaw cycles widen openings, plant roots exploit every weakness. Eventually, entire structures collapse. Those fragments continue weathering until they become little different from ordinary stone and sediment. Glass appears different because it resists many forms of corrosion. Some people imagine glass surviving almost forever. Indeed, certain natural glasses formed by volcanic eruptions have endured for extraordinarily long periods. However, manufactured glass also suffers weathering. Its surfaces slowly react with water. Mechanical forces shatter it. Sediments bury it. Pressure eventually crushes delicate objects into fragments. Even where pieces survive, recognizing them as products of civilization after tens of millions of years could prove extraordinarily difficult. Perhaps the most intriguing material is plastic. Unlike wood, paper, or cloth, many plastics resist biological decay remarkably well. For this reason, modern environmental scientists have become increasingly concerned about plastic pollution within marine sediments, mountain snow, rainfall, river systems, and even within living organisms. Would plastics, therefore, survive tens of millions of years? Not necessarily in recognizable forms. Over immense geological timescales, heat, pressure, chemical reactions, and microbial activity continue altering even these remarkably persisted materials. Some fragments may be incorporated into sedimentary rocks. Others may degrade into simpler compounds. The exact outcome depends upon burial conditions, temperature, pressure, oxygen availability, and countless other environmental factors. The important point is that while individual plastic bottles would almost certainly disappear, unusual concentrations of synthetic polymers or their chemical descendants might potentially leave detectable traces within future geological formations. This distinction lies at the very heart of the Silurian hypothesis.
Scientists do not expect future geologists to discover intact automobiles preserved beneath dinosaur fossils. Instead, they ask whether industrial civilization leaves subtle signatures that outlive its visible structures. Even aluminum, one of humanity's most useful metals, gradually corrodes under many natural conditions. Copper develops protective mineral coatings before eventually becoming incorporated into surrounding geology. Electronic devices, despite their astonishing complexity, depend on delicate components that deteriorate rapidly once exposed to moisture, heat, and biological activity. Computer chips, satellites, smartphones, and electrical circuits may seem revolutionary today, yet measured against millions of years, they are astonishingly fragile. The irony is almost poetic. Some of the simplest objects ever created by nature, tiny fossil shells, grains of pollen, microscopic organisms buried gently within fine sediments, often survive longer than humanity's greatest technological achievements. A delicate leaf pressed into mud under ideal conditions may outlast an entire modern city. This realization shifts our perspective once again. Civilizations do not necessarily endure because they build larger structures. They endure only if the geological record preserves evidence that those structures once existed. The difference is profound. One concerns architecture, the other concerns memory. As scientists continue investigating Earth's ancient rocks, they search not for recognizable streets or monuments, but for faint chemical echoes left behind by industry itself. Subtle clues so small that they can be measured only with sophisticated instruments, yet perhaps so enduring that they remain long after every visible sign of civilization has faded into the quiet landscape of geological time. And it is those invisible echoes, rather than ruined cities, that will guide our next stage of our journey as we begin exploring the remarkable chemical fingerprints that industrial civilizations may leave behind within the ancient pages of Earth's memory.
By now, our journey has carried us across drifting continents, vanished mountain ranges, forgotten coastlines, and cities that, given enough millions of years, could quietly dissolve back into the landscapes from which they were once built. And perhaps the most surprising lesson we have learned is that visible monuments are remarkably fragile when measured against geological time, encouraging scientists to look elsewhere for evidence of technological activity, not among towering ruins or buried roads, but within the invisible chemistry of the Earth itself. Imagine entering a vast library where every book has lost its cover. Many pages have been torn away, and the remaining chapters have become scattered across thousands of shelves stretching farther than the eye can see. Finding a single story within such a library would require extraordinary patience. You would not expect complete volumes. Instead, you would search for recurring words, familiar handwriting, fragments of illustrations, and subtle patterns connecting one surviving page to another. Geologists work in much the same way. The Earth rarely preserves perfect records. Instead, it offers fragments, a thin layer of unusual clay, an unexpected concentration of certain metals, microscopic fossils preserved within limestone, tiny variations in isotope ratios. Each clue appears insignificant alone. Together, they reveal astonishing histories. When scientists ask whether an industrial civilization could leave detectable traces after tens of millions of years, they are not searching for monuments, they are searching for signatures. A signature is not a complete object. It is evidence that something happened. Just as a footprint tells us someone once crossed a beach without preserving the traveler themselves, a geological signature may reveal an event long after every visible trace has disappeared. Our own civilization already produces countless such signatures. Every year, humanity extracts billions of tons of coal, oil, natural gas, iron ore, copper, aluminum,
and countless other resources from deep beneath the Earth's surface. Those materials existed underground for millions of years before industrial activity rapidly redistributed them across the planet. Coal once rested quietly beneath ancient forests, transformed into rock through unimaginable spans of time. Today, much of that carbon has returned to the atmosphere as carbon dioxide through combustion. Oil that remained trapped beneath sedimentary layers since the age of dinosaurs now powers aircraft, ships, factories, and automobiles. In geological terms, this redistribution has occurred almost instantaneously. A future geologist studying rocks formed during our present age might notice that something unusual happened. Carbon concentrations changed rapidly. Certain heavy metals appeared in unexpected places. Artificial compounds became incorporated into sediments. Radioactive elements produced by nuclear technology spread globally in thin but measurable layers. These observations would not immediately identify humanity. They would, however, indicate that Earth's natural systems experienced a sudden disturbance. The challenge lies in distinguishing industrial signatures from natural events. Volcanic eruptions also release carbon dioxide. Asteroid impacts spread unusual minerals across continents. Massive methane releases alter atmospheric chemistry. Forest fires redistribute carbon. Nature possesses many mechanisms capable of producing dramatic environmental changes. Therefore, scientists must ask not whether a single unusual signal exists, but whether multiple independent lines of evidence point towards the same explanation. This careful approach defines modern geology. No single measurement proves a complex conclusion. Instead, researchers compare evidence from many locations. They examine sediments deposited in oceans, lakes, river valleys, and caves. They analyze isotope ratios with extraordinary precision. They measure tiny concentrations of elements that occur naturally in one environment but become unusually abundant when industrial processes redistribute them. One fascinating possibility concerns synthetic compounds. Modern chemistry has produced thousands of molecules that rarely or never existed naturally before industrial manufacturing. Some break down quickly, others persist for remarkably long periods. Could future rocks preserve traces of such compounds? Perhaps. The answer depends upon burial conditions, temperature, pressure, groundwater chemistry, microbial activity, and countless other factors that influence preservation. Yet even if the compounds themselves disappeared, their breakdown products might still leave detectable chemical patterns. Another possibility involves mining. Human civilization has moved enormous quantities of rock. Open-pit mines reshape landscapes visible from space. Tunnels extend beneath mountains. Waste materials accumulate in artificial deposits. Given enough time, these features would erode, yet some geochemical anomalies might remain within sediments transported away from mining regions by rivers and winds. Perhaps the most remarkable realization is that industrial civilizations need not leave dramatic monuments to become visible within geology. A civilization may vanish physically, while its chemistry quietly survives. Invisible fingerprints may endure long after visible hands have disappeared. For this reason, the Silurian hypothesis encourages scientists to think like detectives rather than treasure hunters. Instead of searching for lost cities hidden beneath jungles or deserts, they investigate tiny variations in ancient rocks, trusting that if industrial activity ever altered Earth's natural systems on a global scale, at least some subtle evidence might remain. Whether such evidence exists for a civilization before humanity remains another question entirely. At present, no confirmed geological signature requires such an explanation. Yet by learning how to recognize industrial fingerprints in principle, researchers become better prepared to study both our own planet and distant worlds orbiting other stars.
Among all the invisible clues hidden within ancient rocks, few have proven more valuable to geologists than tiny variations in carbon, an element so ordinary that it forms the foundation of every known living organism, yet so informative that minute changes in its behavior allow scientists to reconstruct climates, ecosystems, and environmental transformations that occurred tens or even hundreds of millions of years ago. Carbon exists in several forms, known as isotopes. They behave almost identically in everyday chemistry, yet differ slightly in mass because their atomic nuclei contain different numbers of neutrons. These tiny differences may seem insignificant, but nature treats them with remarkable sensitivity. Plants, for example, absorb carbon during photosynthesis. In doing so, they tend to prefer one isotope slightly more than another. As living organisms grow, die, and become buried within sediments, those preferences leave subtle patterns preserved within rocks. To the naked eye, such rocks appear perfectly ordinary. To a geochemist equipped with precise instruments, they become detailed records of ancient biological activity. Imagine reading a diary written not with words, but with atoms. Every layer of sediment contains information. Every fossil shell preserves tiny chemical decisions made by organisms millions of years ago. Every grain of limestone records aspects of the seawater from which it formed. Together, these microscopic details create one of the most remarkable archives ever discovered. When humanity burns coal, oil, and natural gas, something unusual happens. These fossil fuels originated from ancient living organisms whose carbon isotope composition differs slightly from much of the atmosphere. Releasing enormous quantities of that carbon changes atmospheric isotope ratios. Scientists today can measure those changes directly. They provide clear evidence that industrial activity has altered Earth's carbon cycle. Now, imagine a geologist living 50 million years in the future. Suppose they examine sedimentary rocks formed during the 21st century. Might they notice a sudden shift in carbon isotope ratios? Very possibly. The change itself would not identify automobiles, power stations, or factories. Yet it could indicate that something rapidly disturbed the global carbon cycle. Interestingly, geology already contains several ancient events involving dramatic carbon isotope changes. One of the most famous occurred approximately 56 million years ago during the Paleocene-Eocene thermal maximum, often abbreviated as the PETM. During this interval, global temperatures rose significantly, ecosystems shifted, oceans changed chemically, and carbon isotope records reveal a substantial disturbance in Earth's carbon cycle. Scientists have devoted decades to understanding this remarkable event. Various explanations have been proposed, including massive volcanic activity, methane release from seafloor sediments, changing ocean circulation, and other natural mechanisms. Importantly, none of the available evidence requires an ancient industrial civilization. Natural processes remain the most convincing explanations. Yet, the existence of such ancient carbon anomalies inspired an intriguing question. If modern industrial civilization produces recognizable isotope changes today, could a future civilization mistakenly interpret an ancient natural event as evidence of technology?
Conversely, if an ancient technological civilization somehow existed, could its chemical signature resemble known natural events closely enough to escape recognition? The Silurian hypothesis explores precisely this uncertainty, not because evidence currently points toward forgotten civilizations, but because distinguishing natural from artificial planetary change proves surprisingly difficult. Carbon is only one clue. Scientists also examine oxygen isotopes, sulfur isotopes, nitrogen cycles, trace metals, and many other chemical indicators. Each contributes another piece of the puzzle. No single measurement provides certainty. Instead, researchers compare multiple independent records from widely separated locations. If all point toward the same conclusion, confidence gradually increases. This method reflects one of science's greatest strengths. Extraordinary questions demand extraordinary careful evidence. Rather than accepting dramatic explanations too quickly, scientists patiently eliminate ordinary possibilities first. Only when natural mechanisms fail completely would more unusual hypotheses deserve serious consideration. So far, nature has continued demonstrating extraordinary creativity. Volcanoes, changing ocean currents, methane releases, continental drift, asteroid impacts, biological evolution. Each has repeatedly transformed Earth's chemistry in ways that sometimes resemble industrial disturbances, while remaining entirely natural. This realization does not weaken the Silurian hypothesis. Instead, it clarifies its purpose. The hypothesis reminds us that planetary chemistry is wonderfully complex. Recognizing intelligence among natural processes requires careful humility because planets possess countless ways of surprising even their most attentive observers.
As evening deepens and our thoughts continue drifting gently backward through the immense history of the Earth, we eventually arrive at some of the most dramatic chapters ever written within the geological record. Chapters marked not by the quiet appearance of new species, but by their sudden disappearance, when vast portions of life vanished in comparatively brief intervals, leaving behind worlds profoundly different from those that came before. These events are known as mass extinctions. Unlike the ordinary background extinction that continuously affects individual species throughout Earth's history, mass extinctions involve global ecological crises during which enormous numbers of organisms disappear across many different environments within relatively short geological periods. The most famous occurred approximately 66 million years ago, when an asteroid roughly 10 kilometers in diameter struck the region now known as the Yucatan Peninsula. The impact released energy beyond ordinary human comprehension. Shock waves spread across continents, wildfires ignited, dust and aerosols entered the atmosphere. Sunlight diminished, food chains collapsed, the age of the non-avian dinosaurs came to an end. Yet this was not the only great extinction. Long before the dinosaurs vanished, Earth experienced several other profound biological crises. The end Permian extinction, occurring around 252 million years ago, proved even more devastating. An estimated 90% of marine species disappeared. Many terrestrial organisms vanished as well. Scientists continue investigating the causes, with enormous volcanic eruptions in what is now Siberia considered one of the leading explanations. Those eruptions released immense quantities of carbon dioxide and other gases.
Global temperatures changed, ocean chemistry shifted, oxygen levels declined, entire ecosystems collapsed before slowly recovering across millions of years. To modernize, these events seem almost apocalyptic. Entire worlds disappeared, yet life endured. New ecosystems eventually emerged. Evolution continued its patient work. Every extinction also became a beginning. Within this context, the Silurian hypothesis asks another thoughtful question. If industrial systems alter planetary systems, could their signatures resemble those produced by natural catastrophes? The answer appears to be yes, at least in part. Industrial activity changes atmospheric composition. Large volcanic provinces also change atmospheric composition. Human emissions influence climate. Asteroid impacts influence climate. Industrial pollution alters ocean chemistry. Natural geological events can produce similar effects through entirely different mechanisms. Therefore, distinguishing between natural and technological causes becomes extraordinarily challenging. Suppose future scientists discovered an ancient layer containing rapid warming, unusual carbon isotope shifts, changing ocean chemistry, and elevated extinction rates. Would that automatically imply industry? Certainly not. Nature has already produced comparable combinations many times. Additional evidence would be required. Researchers would search for synthetic molecules, artificial radioactive isotopes, unusual mineral processing, globally distributed industrial compounds, or other signatures difficult to explain through ordinary geology alone. So far, no ancient mass extinction has yielded such evidence. Every major extinction currently studied finds convincing natural explanations supported by multiple independent observations. This conclusion is important. The Silurian hypothesis does not argue that mass extinctions hide forgotten civilizations. Rather, it demonstrates how difficult planetary detective work truly becomes when multiple natural processes imitate some effects of industrial activity. Perhaps this lesson extends beyond geology into philosophy. Human beings naturally seek stories. We connect events. We search for hidden causes. Sometimes the simplest explanation proves correct. Sometimes reality surprises us. Scientific progress depends upon maintaining enough imagination to ask bold questions while preserving enough discipline to accept ordinary answers whenever evidence supports them. As we reflect upon Earth's lost worlds, another quiet realization emerges. Civilizations, should they ever arise, exist within ecosystems rather than above them. Every society depends upon air, water, climate, soils, oceans, forests, and countless forms of life. When planetary systems change dramatically, civilizations would inevitably change as well. The history of life reminds us that no species, however successful, remains permanently protected from environmental transformation. The dinosaurs ruled the Earth for far longer than humanity has yet existed. Their dominance seemed complete, yet geological history continued. Mammals expanded. Primates evolved. Eventually, humans appeared. Perhaps the greatest message carried by the fossil record is not one of destruction, but of continuity. The Earth changes, life adapts, new chapters begin, old chapters end. the planet patiently continues writing its remarkable story across millions of years, preserving enough clues for future generations to wonder about the past, while quietly reminding every civilization that it occupies only a single page within an astonishingly long and still unfinished book. And with that gentle thought, we prepare to move even deeper into the mystery, where imagination and evidence meet once more, asking not whether an ancient civilization has been found, but what such a civilization would truly have looked like if it had ever existed at all. As our quiet journey continues, the earth beneath our imagination grows older still, carrying us into landscapes where the familiar world disappears entirely, replaced by forests unlike any that exist today, coastlines shaped by vanished oceans, and skies beneath which creatures now known only through fossils lived ordinary lives without the slightest awareness that tens of millions of years in the future, another intelligent species would wonder whether any civilization might have arisen before its own. It is a curious habit of the human mind to imagine history as though it were always moving toward our arrival, almost as if the appearance of humanity had been inevitable from the beginning of Earth's story. Yet, modern evolutionary biology paints a much gentler and far less predictable picture, reminding us that evolution possesses no predetermined destination, no final goal toward which every species slowly progresses, but instead unfolds through countless interactions between chance, environment, adaptation, and time, producing an astonishing diversity of life whose future has always remained wonderfully uncertain. If we could somehow return 100 million years into the past and quietly observe the Earth without disturbing it, we would not find a world preparing for human civilization. We would find a world perfectly complete in its own right. Dinosaurs wandered across broad floodplains, pterosaurs drifted above warm coastal waters, marine reptiles hunted through ancient seas, flowering plants continued spreading across continents, small mammals lived mostly unnoticed in the shadows of far larger creatures. Nothing within that world suggested that one particular lineage would eventually construct telescopes, compose symphonies, write mathematics, or ask philosophical questions beneath distant stars. Indeed, had circumstances unfolded only slightly differently, humanity might never have appeared at all. The asteroid impact that occurred approximately 66 million years ago dramatically altered the course of evolution. By eliminating many dominant species, especially the large non-avian dinosaurs, it opened ecological opportunities that allowed mammals to diversify into forms previously impossible under dinosaur dominance. Over millions of years, those mammals expanded into forests, grasslands, rivers, mountains, and eventually every continent except Antarctica. Among them appeared primates. Among primates emerged hominins. Among hominins eventually arose Homo sapiens. Yet none of these outcomes were guaranteed. If the asteroid had missed the Earth entirely, evolutionary history might have followed an entirely different path. Perhaps dinosaurs would have continued dominating terrestrial ecosystems for tens of millions of additional years. Perhaps mammals would have remained relatively small. Perhaps another lineage altogether would eventually develop higher intelligence. Or perhaps no species would ever build an industrial civilization. These possibilities reveal one of evolution's deepest lessons. Intelligence itself is not the inevitable destination of life. It is one possible outcome among many.
On Earth today, millions of species thrive successfully without constructing technology, writing languages, or altering planetary chemistry through industry. From an evolutionary perspective, humanity represents one remarkable experiment rather than the predetermined purpose of biological history. This understanding becomes particularly important when considering the Silurian hypothesis. If another technological civilization had somehow arisen before humans, there is no compelling reason to imagine that its members would resemble us physically. They need not walk on two legs. They need not possess hands shaped like ours. They need not speak using voices, perceive color in the same way, or organize societies according to familiar human customs. Evolution works with whatever opportunities exist within particular environments. An intelligent species emerging from reptiles, birds, mammals, or some entirely unfamiliar lineage might solve similar problems through completely different biological designs. Yet remarkable constraints also exist. Physics remains the same regardless of species. Gravity affects every organism. Chemistry obeys universal principles. Fire requires oxygen and fuel. Metallurgy demands high temperatures. Energy production follows physical laws. Any technological civilization developing advanced technology would almost certainly encounter many of the same practical challenges humanity has faced, even if its solutions differed greatly. The question therefore shifts. Rather than asking whether another civilization would resemble humans, perhaps we should ask whether technological development itself leaves recognizable planetary consequences, regardless of the biological form of the civilization responsible. This thought connects beautifully with the scientific purpose of the Silurian hypothesis. Researchers do not search for human-shaped fossils carrying tools. They search for planetary signatures. Civilizations may differ. Planets obey common physical laws. In that sense, the Earth itself becomes the shared language through which any technological society, however different from humanity, might inadvertently communicate across millions of years. The rocks do not record whether engineers possessed feathers, scales, fur, or skin. They record changes in carbon cycles. They preserve sediments. They remember chemistry. Perhaps this perspective offers quiet comfort. The history of life is not merely a sequence of winners replacing losers. It is an ongoing tapestry woven from countless possibilities, many realized, many forever unrealized, each contributing to the astonishing richness of Earth's long biological journey. Having considered that intelligence might emerge in many different biological forms, we now arrive at perhaps the most imaginative stage of our exploration. Not because we intend to replace science with fantasy, but because careful speculation, when clearly separated from established evidence, often helps illuminate the assumptions hidden within our own thinking, revealing how deeply our expectations about civilization are shaped by the particular path humanity itself has followed. When most people hear the word civilization, familiar images immediately arise. Towering cities, stone monuments, roads stretching toward distant horizons, libraries, ships crossing oceans,
great monuments illuminated beneath the sun. These images feel natural because they belong to our own experience. Yet they may represent only one among countless possible expressions of technological society. Consider for a moment how strongly every human city depends upon the specific conditions of our planet. We breathe an oxygen-rich atmosphere. We live upon continents separated by oceans. Our ancestors discovered fire because dry wood, oxygen, and lightning existed together. Agriculture developed because certain grasses proved suitable for domestication. Metals became valuable because geological processes concentrated useful ores within accessible deposits. Had any of these conditions differed substantially, civilization itself might have taken another form. A hypothetical pre-human civilization would likewise develop according to its own environment. If it inhabited shallow tropical seas, maritime technology might dominate its history. If it inhabited volcanic islands rich in geothermal energy, perhaps heat rather than fossil fuels would become its principal resource. If intelligence evolved within highly social marine animals, technological development might proceed along paths almost impossible for terrestrial humans to imagine. Yet, however different such societies might appear, certain universal requirements likely remain. Advanced technology demands energy. Complex societies require communication. Large populations depend upon stable food supplies. Knowledge must somehow pass between generations. Materials must be gathered, transformed, and transported. These practical necessities arise not from human culture alone, but from the fundamental realities of physics and biology. For this reason, many scientists believe that any industrial civilization, regardless of its biological origins, would eventually begin altering its environment in measurable ways. Energy consumption changes atmospheric chemistry. Mining redistributes minerals. Agriculture transforms landscapes. Transportation connects distant regions. Manufacturing introduces new compounds into natural systems. The exact technologies might differ enormously. The planetary consequences could still display recognizable similarities. Interestingly, humanity itself demonstrates how quickly such transformations can occur. For thousands of years, our ancestors lived primarily as hunter-gatherers, whose environmental influence remained relatively localized. Agriculture expanded that influence. Cities intensified it. Industry accelerated it dramatically. Within only a few centuries, atmospheric carbon dioxide increased substantially. Rivers were redirected. Forests disappeared across vast regions. Artificial materials spread globally. Never before in Earth's history had one species altered planetary systems so rapidly. Would another civilization necessarily follow the same trajectory? Not at all. Perhaps it would discover sustainable energy much earlier. Perhaps it would remain relatively small. Perhaps cultural traditions would discourage large-scale environmental transformation. Perhaps available natural resources would lead toward entirely different technological pathways. The Silurian hypothesis does not assume that every civilization resembles modern industrial society. Instead, it asks what evidence survives if a civilization does significantly modify planetary processes. This distinction deserves careful attention. The hypothesis concerns detectability, not inevitability.
An ancient civilization could theoretically remain almost invisible if it never reached an industrial stage capable of producing global environmental signatures. Likewise, a civilization that flourished briefly before disappearing might leave only the faintest geological trace, difficult or impossible to distinguish from ordinary natural variability. There is another possibility as well, one that feels surprisingly peaceful. Perhaps technological sophistication does not always require endless expansion. Perhaps truly advanced societies eventually learn to integrate more gently with planetary systems rather than reshaping them ever more dramatically. If so, the civilizations easiest to detect across geological time might actually represent those passing through relatively brief periods of intense environmental transformation, much like humanity today. Whether this idea proves true remains unknown, yet it gently reminds us that our own civilization may occupy only one chapter within a much broader range of possibilities. When imagining forgotten worlds, we should therefore remain cautious. The greatest obstacle to understanding hypothetical civilizations is often not the absence of evidence, it is the tendency to imagine every unknown society as a reflection of ourselves. Science invites us to do something more difficult, to imagine carefully, to remain humble, and to recognize that reality often proves more creative than expectation. There is a certain quiet beauty in accepting that some questions may never receive complete answers, not because they lack importance, but because the universe itself preserves only fragments of its immense history, leaving future generations to reconstruct the past from scattered clues, while understanding that certain pages have been permanently lost. Throughout our journey, we have watched mountains disappear, oceans recycle their floors, rivers bury civilizations, rocks transform beneath heat and pressure, and chemistry preserve memories invisible to ordinary sight. Together, these processes reveal an extraordinary truth. The Earth remembers, but it remembers selectively. Imagine walking through an ancient forest after a gentle snowfall. At first, every footprint appears perfectly clear. Hours later, fresh snow begins covering the earlier tracks. Days pass. The wind reshapes the surface. Soon, no visible evidence remains that anyone ever walked there at all. Yet the travelers undoubtedly existed. Their absence from the snow no longer reflects their absence from history. Geological time behaves similarly. Events occur. Many leave traces. Some traces survive. Others disappear forever. The challenge lies in distinguishing between events that never happened and events whose evidence has simply been erased. Scientists confront this challenge every day. Entire species are known from only a single fossil. Ancient ecosystems remain incomplete because preservation favored some organisms while overlooking others. Soft-bodied animals rarely fossilize. Mountain environments preserve less evidence than quiet lake bottoms. Oceanic crust older than about 200 million years has largely been recycled into Earth's mantle. The archive is remarkable. It is also incomplete. Suppose, purely as a thought experiment, that an industrial civilization had arisen 150 million years ago. Its largest cities stood primarily upon coastlines now consumed by subduction. Its artifacts weathered away, its metals oxidized, its concrete crumbled,
Its plastics degraded. Its sediments were later metamorphized by heat and pressure. After millions upon millions of years, what would remain? Perhaps nothing recognizable. Perhaps only subtle chemical anomalies. Perhaps not even those. This possibility does not demonstrate that such a civilization existed. Rather, it illustrates the limits of geological preservation. Some histories simply become inaccessible. This realization carries important philosophical implications for science. Researchers cannot conclude that something occurred merely because evidence might have disappeared. Neither can they conclude with absolute certainty that it never occurred, solely because direct evidence remains absent. Instead, science operates within probabilities. Conclusions strengthen as evidence accumulates. They weaken when evidence fails to appear where it reasonably should. Current evidence strongly supports the understanding that humanity represents Earth's first known industrial civilization. No convincing geological signatures require another explanation. Yet acknowledging that conclusion does not eliminate the value of the Silurian hypothesis. Quite the opposite. The hypothesis sharpens scientific reasoning by forcing researchers to examine what kinds of evidence industrial activity should actually produce. It improves methods used to interpret ancient rocks. It informs the search for extraterrestrial civilizations. It deepens our understanding of Earth's own history. Perhaps equally important, it teaches intellectual humility. There is a profound difference between saying, "we have no evidence," and saying, "something is impossible." Science rarely speaks in absolutes. Instead, it continually refines its understanding as new observations emerge. Most discoveries confirm existing knowledge. Occasionally, one transforms it entirely. The greatest scientists often display remarkable comfort with uncertainty. They understand that unanswered questions are not failures, they are invitations, quiet doors left slightly open for future generations. As evening settles more deeply around us, it becomes comforting to realize that mystery itself possesses value. Not every unanswered question demands immediate resolution. Some encourage patience. Some inspire curiosity. Some remind us how vast the universe truly is. Whether or not another civilization ever walked upon the Earth before humanity, the planet has already lived a history so immense, so dynamic, and so astonishing that it scarcely requires additional wonders to earn our admiration. The continents alone have traveled farther than any human explorer. The oceans have written stories older than memory. The rocks have preserved chapters spanning billions of years. And hidden among those ancient pages remain countless discoveries still waiting for careful minds to uncover them, perhaps with time. Perhaps the greatest lesson offered by the Silurian hypothesis is not that a forgotten civilization once existed. It is that the Earth is capable of keeping secrets with extraordinary patience, revealing them only gradually to those willing to listen, not for dramatic revelations, but for the quiet whispers preserved within stone, chemistry, and the slow rhythm of geological time. With that gentle understanding, our exploration of the distant past begins turning slowly toward the present, where another question quietly awaits us. If future scientists were to study the rocks created during our own age, what story would they discover about us?
As our long and peaceful journey through the immense history of the Earth gradually begins turning toward the present, we arrive at a quiet realization that feels both deeply personal and strangely humbling. Because after spending so much time wondering whether another civilization might once have walked across this ancient planet long before humanity appeared, we eventually discover that the most fascinating geological mystery may not belong to the distant past at all, but rather to the present moment in which we ourselves are living. For every road we travel, every city we build, every field we cultivate, every bridge that stretches across a river, every tunnel carved beneath a mountain, and every object we quietly leave behind is already becoming part of the geological record that future geologists, living perhaps 50 million years from now, would somehow be able to examine rocks formed during our own era. Human beings often imagine history as something safely behind us, carefully preserved inside museums, libraries, and monuments. Yet geology understands history differently, because the Earth's archive is not something completed long ago, but something continuously expanding every hour of every day as new layers of sediment settle upon riverbeds. Tiny shells drift gently toward the seafloor. Volcanic ash occasionally blanket distant landscapes. Glaciers slowly transport stones across valleys, and microscopic particles produced by modern civilization quietly become incorporated into soils, lakes, and oceans, joining an archive that has been growing almost without interruption for billions of years. At this very moment, while countless people sleep peacefully across different continents, rivers continue carrying sediments toward the sea. Ocean currents distribute tiny fragments of natural minerals and manufactured materials alike. Pollen settles upon quiet lakes. Leaves sink into wetlands. Coral animals patiently construct reefs beneath warm tropical waters, and the atmosphere itself records every subtle change in its chemical composition, demonstrating that the Earth never pauses its quiet work of remembering, even while those living upon its surface remain almost entirely unaware that tomorrow's geological record is already taking shape beneath their feet. If future geologists, living perhaps 50 million years from now, were somehow able to examine rocks formed during our own era, they would almost certainly notice that something unusual occurred within an extraordinarily brief interval of geological time. Because compared to the slow natural rhythms that typically characterize Earth's history, the industrial age resembles a sudden flash of activity during which atmospheric chemistry changed rapidly. Fossil carbon returned to the atmosphere in remarkable quantities. Artificial materials spread across nearly every environment, and the distribution of many elements became unlike anything observed throughout much of the preceding geological record. They might observe a thin layer enriched with microscopic plastic fragments whose original shapes had long since disappeared, but whose chemical descendants remained faintly preserved within sedimentary rocks. They might detect unusual concentrations of aluminum, copper, lead, chromium, rare earth elements, or industrial alloys redistributed far beyond their natural locations where geological processes originally concentrated them. They might notice globally distributed radioactive isotopes produced by 20th century nuclear testing, leaving behind one of the most distinctive chronological markers humanity has ever unintentionally created.
They would likely identify a sudden alteration in carbon isotope ratios corresponding to the rapid combustion of fossil fuels that had remained buried beneath the Earth for tens or hundreds of millions of years before being released again within only a few centuries. Perhaps they would also discover traces of synthetic organic molecules, unlike those normally produced through natural biological processes, some surviving directly, others preserved only through the subtle chemical transformations they initiated within surrounding sediments. Taken individually, none of these observations would necessarily prove the existence of an industrial civilization. Nature is wonderfully inventive. Volcanoes alter atmospheric chemistry. Meteorite impacts scatter unusual materials. Large forest fires redistribute carbon. Changing ocean circulation modifies climate. Yet when many independent observations point toward the same remarkable interval, the broader picture gradually becomes clearer. Future scientists, much like those working today, would assemble countless tiny clues rather than relying upon a single dramatic discovery. In this way, our civilization is quietly writing its own geological autobiography. Not intentionally, not consciously, but inevitably. Every generation contributes another paragraph. Every technological advance leaves another sentence in the story. Every environmental change adds another line to the story. Long after languages evolve beyond recognition, nations disappear, political boundaries fade, and every familiar building has returned to stone and soil, those subtle geological signatures may continue speaking on our behalf. The thought carries neither pride nor regret. It simply reminds us that civilizations do not vanish without consequence. They become part of the earth itself. The rocks beneath future feet may one day whisper that, for a remarkably brief moment within geological time, one species learned to reshape an entire planet.
Perhaps the greatest gift offered by the Silurian hypothesis is not the possibility of discovering a forgotten civilization hidden somewhere within Earth's ancient rocks, but the unexpected opportunity to view our own civilization from an unfamiliar perspective, one so distant in time that many of the concerns occupying our daily lives become almost invisible, allowing us to recognize patterns that are otherwise difficult to see while living within them. Human history often feels extraordinarily important because it is the history we know. Empires rise, empires fall. Ideas spread across continents. Technologies transform daily life. Generations inherit knowledge accumulated over thousands of years. Each event seems significant because it shapes the experiences of those living through it. Yet when viewed from the perspective of geological time, the entire history of civilization becomes astonishingly brief. Imagine compressing the entire 4.5 billion year history of Earth into a single calendar year. The first oceans would appear early in the year. Complex life would emerge much later. Dinosaurs would dominate during the final weeks of December. Modern humans would arrive only during the last minutes of December 31st. Recorded history would occupy merely the last seconds before midnight. The Industrial Revolution would occur so close to the final stroke of midnight that it would scarcely register as more than the briefest flicker. This comparison is familiar to many geologists because it illustrates something profoundly important. Human civilization has accomplished extraordinary changes within an almost unimaginably short interval.
Never before, so far as current evidence reveals, has a single species altered atmospheric chemistry, global ecosystems, ocean composition, river systems, and landscapes with such speed. Whether future historians celebrate these changes, criticize them, or simply describe them objectively remains unknown. Geology itself expresses no judgment. It merely records. The rocks neither praise nor condemn. They remember. This perspective encourages humility. The buildings we admire today will not stand forever. The technologies that seem revolutionary will eventually become obsolete. Languages evolve. Cultures transform. Even the coastlines surrounding our great cities continue changing with quiet persistence. Nothing remains entirely fixed. Yet impermanence should not be mistaken for meaninglessness. A flower blooming for a single morning still possesses beauty. A melody lasting only a few minutes may remain unforgettable. Likewise, the brevity of civilization within geological time does not diminish its significance. Rather, it highlights the extraordinary ability of intelligent life to influence a planet despite occupying only a tiny fraction of its history. Perhaps somewhere among the countless stars scattered across the universe, another civilization is asking questions remarkably similar to our own. Perhaps astronomers on a distant world study their planet's geological record while wondering whether earlier societies once flourished before disappearing into deep time. Perhaps they too struggle to distinguish natural planetary changes from technological ones.
Perhaps they too have developed thought experiments, much like the Silurian Hypothesis, using their own world's history to improve the search for intelligence elsewhere. Whether such civilizations exist remains unknown, yet imagining them gently expands our perspective. It reminds us that curiosity itself may be one of intelligence's most universal qualities. The desire to understand origins, the patience to examine evidence, the willingness to question assumptions. These habits connect scientists across cultures, generations, and perhaps someday even across worlds. The Silurian Hypothesis, therefore, becomes something larger than a question about ancient Earth. It becomes a meditation on knowledge itself. How do we know what we know? How reliable is the evidence preserved by nature? What stories remain forever hidden because time erased the necessary clues? And how should thoughtful people respond when certainty proves impossible? Science offers a beautifully simple answer. Remain curious. Remain careful. Accept uncertainty where evidence requires it. Follow observations wherever they lead. In doing so, we honor not only the search for truth, but also the extraordinary planet that has preserved enough of its history to make such questions possible. As our evening journey approaches its quiet conclusion, let us leave behind laboratories, geological surveys, isotope measurements, tectonic plates, and scientific hypotheses for just a few peaceful moments, returning instead to something far older and wonderfully familiar. The simple experience of standing beneath a clear night sky, where the stars shine with the same gentle light that has illuminated countless generations, stretching backward through history, and far beyond it into ages when humanity had not yet appeared. Imagine yourself standing upon a quiet hillside long after sunset. The air is cool. A soft breeze moves gently through the grass.
Somewhere in the distance, an owl calls into the darkness before silence slowly returns. Above you stretches an immense canopy of stars. Many of those stars formed long before the Earth itself existed. Their light began its journey across space years, decades, centuries, or even thousands of years before reaching your eyes tonight. Among them are worlds we have never seen, planets we have never visited, perhaps oceans no telescope has yet observed, perhaps continents forever hidden by distance, perhaps places where life never emerged, perhaps places where it quietly flourishes, perhaps somewhere unimaginably far away, another curious species has also looked upward, wondering whether it stands alone in the universe. The Earth beneath your feet has witnessed almost 4.5 billion years of change. It has survived asteroid impacts, volcanic cataclysms, drifting continents, frozen ages, tropical climates, rising mountains, disappearing oceans, and countless evolutionary experiments that succeeded for a time before yielding gently to those that followed. Life has transformed the atmosphere. Oceans have advanced and retreated. Species have appeared. Species have vanished. Yet through every transformation, the planet continued turning quietly beneath the stars. Against such immense history, humanity's story remains remarkably young, and yet it is no less extraordinary. Within only a brief geological moment, one species learned to ask questions about atoms, galaxies, fossils, and time itself. It learned to measure the age of rocks, to reconstruct vanished ecosystems, to discover planets orbiting distant suns, to wonder whether another civilization might once have existed long before its own. Perhaps that capacity for wonder is among the most remarkable achievements of all. The Silurian hypothesis does not conclude by revealing hidden cities buried beneath dinosaur bones. It does not uncover forgotten empires sleeping beneath ancient mountains. It offers no evidence that an industrial civilization existed before humanity. Current scientific evidence continues to support the understanding that humanity is Earth's first known technological civilization. Instead, the hypothesis accomplishes something quieter. It reminds us that asking thoughtful questions, even unlikely ones, often leads toward deeper understanding. By wondering whether ancient civilizations could disappear almost without trace, scientists learned more about geology. They refined methods used to study climate. They improved approaches for searching for intelligent life beyond Earth. They gained new appreciation for the extraordinary complexity of the geological record. Sometimes the greatest discoveries arise not from finding unexpected answers, but from asking unexpectedly useful questions. The Earth remains filled with mysteries. New fossils await discovery. Unknown species remain hidden within rainforests and oceans. Ancient climates continue revealing their stories through chemistry preserved in stone. Every generation inherits unanswered questions alongside accumulated knowledge, and every generation contributes something new before quietly passing the search onward. Perhaps millions of years from now, another intelligent species, whether descended from humanity, evolved independently upon Earth, or arriving from some distant corner of the galaxy, will examine rocks formed during our present age. Perhaps they will recognize the subtle fingerprints we leave behind. Perhaps they will wonder about the people who built cities beside rivers, crossed oceans beneath sails and engines, gazed through telescopes toward distant galaxies, and spent peaceful evenings imagining histories far older than themselves. Or perhaps the Earth will keep some of its secrets forever. There is beauty in that possibility too. Not every mystery must be solved. They simply remind us how vast existence truly is.
Now, as our journey gently comes to rest, allow the immense span of geological time to drift quietly into the background, like distant waves settling upon a calm shoreline beneath the soft light of the moon. Feel the reassuring steadiness of the Earth beneath you, a planet that has patiently carried mountains, forests, oceans, deserts, and every living creature through billions of years of continuous change, without ever rushing, without ever forgetting its quiet rhythm. Notice how peaceful that rhythm feels. The continents move, but so slowly that no human lifetime can witness their journey. Mountains rise, but only over millions of years. Rivers shape valleys one drop at a time. Even the stars above continue their silent motion with extraordinary patience. Nature has never hurried. Perhaps there is comfort in knowing that the universe itself unfolds gently. Questions need not all be answered tonight. Some may wait years, some centuries, some perhaps forever. The Earth is content to keep its oldest memories within layers of stone, revealing them only little by little to those who observe carefully and patiently. As your breathing grows slower and more relaxed, imagine the countless generations who have looked toward the night sky before you. Ancient hunter-gatherers resting beside glowing fires, farmers watching the first stars appear above quiet fields, sailors navigating moonlit oceans, astronomers patiently recording the movements of distant planets, geologists kneeling beside weathered cliffs, reading histories written not in ink but in stone. Each belonged to a different moment. Each lived only briefly, yet together they formed one continuous story stretching across time. Tonight you have become part of that story as well, not because you solved every mystery, not because every question found an answer, but because for a little while you allowed yourself to wonder. And perhaps wonder itself is one of the oldest companions humanity has ever known. So let the stars remain where they have always been. Let the mountains continue their slow conversation with the wind. Let the oceans breathe gently against distant shores, and let the earth keep turning quietly beneath the endless night sky, carrying tomorrow toward us with the same patient rhythm that has guided every sunrise for billions of years. Thank you for joining this peaceful journey through deep time. May your thoughts become lighter, may your breathing become slower, and may you drift gently into a restful sleep beneath the same ancient stars that have watched over our remarkable planet since long before the first page of human history was ever written. Good night.